So now we welcome our next speaker, Sezen Sekman from Kyungpook National University, and her topic of talk is, she will talk about high luminosity LHC perspective. Sezen? Okay. Go ahead, Sezen, and I will request you, we are fashionably late, our mistake. So please maintain the time, Sezen. Thank you.
I have a timer standing next to me, so I hope that won't be a problem. Okay, hello everyone. Let me briefly show myself and then to say hi, and then I'll turn off the camera because I have to get close to my slides. Indeed, I will be talking today about the HL-LHC perspectives, physics perspectives. And actually, during this workshop, you have seen many of the pieces that make up my talk. And what I will try to do here is to bring them all together and paint a picture of future for you. So we are right now at the end of, between run 2 and run 3 of the LHC, and we are still analyzing the run 2 data, and we are starting to design run 3 analysis, but at the same time we are doing our best to see what we are to expect physics-wise from HL-LHC, which is going to start in a few years, hopefully around 2020. 25, and it will have a center of mass energy of 14 TeV and an instantaneous luminosity of 5 times 10 to 34 and a total luminosity of about 3 to 4 inverse attobarns, and we expect a lot of pile-up there. Now, this upgraded LHC will bring a lot of opportunities. So since we will have more data, we will have lower statistical uncertainties and lower experimental systematic uncertainties and lower uncertainties on background prediction methodologies. What's more, we will even have improved detectors, new detectors, improved detector coverage and new detector features. But this doesn't come for free. All this new data and increased energy and luminosity also bring some challenges like high pile-up, like high beam-induced backgrounds and high radiation. Therefore, we will need to improve our techniques on analysis, such as on triggering, on object reconstruction, and even our analysis methodologies. Now, there are a lot of upgrades being done on the LHC detectors, and Frank will give a detailed talk on these this afternoon. So only just a brief brush up. So this is showing CMS for which I work. We are expecting, for example, improved coverage of the muon detector, so we'll be able to detect muons at higher ETAs. We will have a new precision timing detector and a new inner tracker and new end cap calorimeter, updates to calorimeters and triggers, data acquisition system, and updates to beam radiation instrumentation and luminosity detectors. Again, Frank will summarize all these. And ATLAS will have similar improvements in their sub-detectors. So all these developments have been documented very nicely in technical design reports written by both experiments. Now, coming to physics studies, we've been working on trying to explore all these new features that HL-LHC and detectors are going to bring us. So there'll be dedicated studies. There are dedicated studies for this. For example, during 2017 and 18, there was a collaboration of LHC experimentalists and theorists, which resulted in so-called CERN yellow report summarizing all the physics potential. So you can find those for standard model Higgs and beyond the standard model referenced here. And there have been several recent technical design reports, as referenced in the previous slides. And finally, currently we have the SNOMES 21 effort going on, and there are again several studies done by LHC experiments, which are showing the new HL-LHC physics studies. And the focus of these studies are to either continue or improve the current searches or to design new searches that explore the high luminosity and detector features. For example, I would like to develop innovative analysis techniques that access scenarios with lower cross sections and lower acceptance, or we would like to open new search channels. So how do we do these studies? What's the methodology? There are two ways. We either do projections from already existing analysis. So this we do when we have an existing analysis which is really relevant and we don't necessarily need to do anything much, and only scaling to the luminosity would be enough. So we just, in this case, we just take all of the results that we have, all the histograms, counts, etc., and then we scale them with the luminosity and the 14 TV cross sections, and then we recalculate our results and the interpretation. But in many cases, we are interested in building new analysis. So we want to look for a new channel. We want to explore a new detector feature, etc., etc. So in this case, we really use dedicated Monte Carlo produced for phase 2 for HL-LHC. And this Monte Carlo could be either the official GEANT-based full detector simulation, or it could be based on DELFES, which you might be already familiar with, which is a parameterized detector simulation tuned using the official experimental simulation packages. And in all these studies, of course, uncertainties are very important in experimental studies. So we use different scenarios of systematic uncertainties, various options. So we either see what we would expect to have if all the run 2 systematic uncertainties were kept the same, or we use a set of reduced systematic uncertainties, which we call the yellow report 18 uncertainties, where the run 2 uncertainties are scaled down in accordance with anticipation for phase 2. So, for example, we scale theory uncertainties by 1/2, etc., etc. Some statistics-driven uncertainties by square root of luminosity, etc. Or we also check the case where we have statistical-only uncertainties. So in this table, I show an example from one SUSY analysis for phase 2, and this shows how the various uncertainties were scaled down for the signals and for the background cases. Okay, now let's start with the physics prospects. First, let's go over what we expect for Higgs. Actually, I think Jyotsna gave a very nice summary of the standard model and Higgs expectations. So these are just to remind you, summarize the results and remind you. So the very first thing we do, of course, is to measure the Higgs cross-section and the branching ratio. And here, just as a reminder, at phase 2 at HL-LHC, we are expecting to have measurements with less than about 5% uncertainty. So this is going to be a very good improvement. But so this means that the theory uncertainty remains dominant for most measurements. And same goes for the Higgs coupling modifier and modifier ratio measurements. Detailed studies have been done by ATLAS and CMS, and combinations were also done. Again, here HL-LHC allows to have reduced uncertainties for the couplings and coupling ratios. Now, HL-LHC will also allow a lot of differential Higgs cross-section measurements. All this data will be very useful for this. So here you can see, again, several examples for these cross-section measurements. Will be exciting to see what we will observe, and maybe, who knows, we will observe some discrepancies. And again, another summary slide, Higgs, which is actually very important at HL-LHC. It's what we call a flagship measurement, because we cannot observe this at run 2 or at run 3, and we really need this HL-LHC for these Higgs measurements. And we also need to combine both ATLAS and CMS results. So here we see the summary of measurements for at the GGH channel, and we expect around 4 sigma from ATLAS plus CMS measurements. Okay, that's it for the standard model Higgs, I think, which was covered by Jyotsna. Now going on a little bit more to the beyond the standard model Higgs realm. So one of the signatures of BSM Higgs would be to see an significant branching ratio of Higgs to invisible decays, because in the standard model, the Higgs to invisible decay branching ratio is about 0.1%. So this is a powerful probe for beyond the standard model physics, for example, light-dark matter coupling to Higgs, etc. And the current run 2 limit is on this branching ratio measurement is about 20% or so in their measurements in different channels. And the easiest way to measure this branching ratio is in conjunction with some taggable objects such as Z or forward jets or high PT jets, etc. And there was a dedicated study done by CMS based on simulation. And it was looking at the vector boson fusion channel, which is the most sensitive channel. And this had a final state of 2 forward jets and missing ET. And despite the Higgs decaying invisibly, this channel has low missing transverse energy. So the analysis was optimized, particularly for HL-LHC, and it required a dye jet invariant mass of 2.5 TeV. And the plot show here the various exclusion limits on the Higgs to invisible branching ratio versus minimum missing ET cut. So the left plot shows how much systematics dominated this analysis is, and the right plot shows the change of the exclusion limit versus the luminosity. Now, for higher missing ET cuts, as we can see, especially the luminosity increase in luminosity is really making a big effect. Now, coming to BSM Higgses, for the heavy neutral Higgs, I guess everyone here now is, sorry, was there a question?
I wanted to know whether you take questions in the middle or at the end.
Yeah, go ahead. I mean, for me, it's fine. If it's fine with the
let me ask Rajesh. Rajesh?
Carry on.
Okay, can you go back to the earlier slide?
Mm-hmm.
I wanted to understand the statement you made about the measurement being systematics dominated. So the idea being is that I lose my sensitivity because if I lower the minimum threshold on the ET miss, I tend to get more and more dominated by systematics. Is that your, so to increase the sensitivity, I need to decrease the minimum threshold. And is that why you are saying systematics dominated? I wanted to know the answer.
Yeah. Well, I mean, so left plot says it all, right? You can see the huge uncertainty band, and the uncertainty band even covers all the luminosity ranges in the right plot.
That is a good point.
It was really a like very generic statement.
Okay,
and actually, for the lower met cuts, it's a little bit better, and for the higher cuts, it's even worse.
No, I see the point you made, that therefore the gain that we are saying luminosity will make is really in some sense only illusory. Okay. No, thanks for this very important.
Yeah, maybe we find another thing. I don't know.
No, good. Okay. Thank you very much. Thank you.
Moving to heavy neutral MSSM Higgses, I think I don't need to introduce MSSM Higgses here. There were, of course, in round 2, again, we have tons of searches for the heavy neutral Higgs, but for HL-LHC, both ATLAS and CMS tried the basic searches in the Higgs to the heavy Higgs to tau. And you can see the results here. So they have different BTAC, BWETO categories. They were looking at leptonic or hadronic tau final states. And the right side plot is showing the enhancement in sensitivity. So the blue shaded area is run 2. Okay, even though it's 36 inverse femtobarn, well, there it improved a little bit, but there's still a lot of way to go for HL-LHC. Then finally, for light Higgses in 2HDM plus singlet models. So again, I'm not introducing the theory motivation here, but NMSSM is very well motivated. So in this case, we are expecting a light Higgs, which is interesting to look for. And our 125 Higgs is decaying to 2 light Higgses, which in turn decay to various combination of standard model particles. So again, in run 2, there are many searches in all sorts of combinations of final states. But here I'm just showing a case for 2 searches, 2b2 tau and 2mu2 tau. And we are seeing the different exclusion curves for the various, let's say, various luminosity options in here. And again, we see how HL-LHC is improving. Now, briefly moving to standard model prospects, there's one interesting projection study on the diboson scattering, a recent study. So this projected WWWZ electroweak scattering process measurements in the leptonic decay mode. And here we can see that there is, well, here we can see how the luminosity increase is increasing the expected significance on the cross-section measurement, literally, and then also let's say the uncertainty decrease again by increasing luminosity. So this was quite an interesting new search from CMS, new study from CMS. And of course, top is one very big point for HL-LHC. Rare processes with tops are important probes of new physics. So 4 tops is quite interesting, of course. We expect 10 to 30% uncertainty, and currently only projections are done, but of course there's room for really developing dedicated searches which will even improve these measurements. And but again, so in this plot we see how the significance is changing with respect to integrated luminosity, and for different systematic scenarios you can see what a difference it makes if we were able to get rid of all the systematic uncertainties. Then we have the associated production of top pairs with WZ and gamma. So there we have differential measurements, and so you can see for TTZ and TT gamma. Again, for TT gamma, we can see the uncertainties here in this plot versus photon PT, and again for HL-LHC, the uncertainties are really significantly decreasing. Now moving to BSM prospects, starting with SUSY. So there were several SUSY simulation and projection studies done. So starting with the stop pair production in the hadronic top decays, there was a simulation study by ATLAS looking at multi-jets plus B-jets plus missing ET, and this was an optimized analysis. Both look for both large mass differences and also for the stop corridor region, and the exclusion would go up to 1.7, whereas for run 2 it's now around 1.2 or so with the full run 2 searches. Another study was looking at gluinos and stops in the 3rd generation final states with hadronic boosted Ws and tops and missing ET and jets. And this was again moving the gluino and stop exclusions up to 2.6 and 1.5 TV. And remember, this is only looking at the boosted channels. Now, staus would be quite relevant for High Luminosity LHC. So here are two examples from ATLAS and CMS, where 2 hadronic taus or 1 hadronic plus 1 lepton plus missing ET final states were analyzed. And we do have various limits, about, let's say, on average 700 GeV. ATLAS limits were better for this study because tau identification was actually optimized. And this shows us that obviously optimizing the analysis, optimizing the objects will leave much more room for improved sensitivity. Going to charginos and neutralinos. So here are several results showing the reach, the exclusion and discovery reaches in 3 different final states. So chargino production going to 2 leptons plus missing ET via WW. And by the way, in all cases, chargino 1 is pure Vino and neutralino 1 is pure Vino. Yes, in all cases it's that way. So this was the first one. The second analysis is chargino 1 neutralino 2 production in the 3 lepton plus missing ET via WZ decays. And the third one is chargino 1 neutralino 2 production in the 1 lepton BB plus missing ET, where the decay happens via WH. So again, in all cases, well, in the first case, the exclusion goes up to 840 GeV, and in the other two, we can exclude above 1.1 GeV and 1.3 GeV. Now, here's a search that was really designed from scratch for HL-LHC, and that's looking for heavy charginos and neutralinos. In this case, we have a same sign dilepton plus missing ET search. And so this is a unique signal again. So this is something that we cannot observe at run 2, obviously. And the analysis, like the dedicated analysis, was able to find out that we would exclude the heavy neutrinos and neutralinos and charginos up to about 900 GeV for different cases of neutralino 1 mass here. And somehow they also managed to extract that by looking at these analysis results, HL-LHC has the potential to probe most of the natural SUSY space with the electroweak naturalness score less than 30, which was proposed by Haviber et al. Now, long-lived particles and SUSY combining, and when we are trying to look for compressed spectra and Higgsinos. So Higgsinos are very important for naturalness again. So and there are 2 ways we can look for Higgsinos. One way is, well, before I say that, I should remind, of course, that the Higgsino signatures are usually compressed. So there's very small mass difference between the second, let's say, the neutralino 2 and the chargino 1 in many cases. Sorry, the neutralino 2, chargino 1, and the neutralino 1. Therefore, we need to build analyses that are really targeting these low mass differences. And going back, I can say that there are 2 ways. Either we, for the case when the mass difference is a bit larger, we can explore the prompt light chargino decays, and we can look at soft lepton analysis. So the prompt charginos or second neutralinos, which have Higgsino components, would decay through soft leptons, and we could look at those soft leptons and missing ET. And the other case, when we have a smaller mass difference, there would be long-lived chargino decays, and the chargino would decay in the tracker, and we would see a disappearing track signature. So ATLAS did a nice combination of all these searches, both of these searches, and put them in the same plot. So the blue, let's say, area is showing the soft lepton searches, and then the light, the yellow area is showing the disappearing track search results. Now, going to long-lived particles, we have, here we are looking at displaced objects. There are several searches done for displaced muons, for example, looking for long-lived muons, as we can see in the diagram here. And there's another search looking for displaced dimuons even. So these are long-lived dark photons coming from Higgs decays. And here there was a special muon reconstruction using only the CMS muon system, but not using the tracker here. And here we can see the exclusion limits on cross-sections or cross-section ratios versus C tau. And then also there was a search on displaced vertices by ATLAS, looking at long-lived gluinos, for example, split SUSY that we just heard about. And they did a displaced vertex RICO in the new ATLAS inner tracker. So one new feature and very important feature is in HL-LHC is the phase 2 timing detectors. Both ATLAS and CMS are getting one. And here are some example searches exploiting these timing detectors. So we would, one search is looking at displaced photons from GMSP. And here we are talking about CMS MIP timing detector, which has a 30 picosecond precision and acceptance below eta smaller than 3. So here we use time of arrival of photons in the MIP timing detector to discriminate signal and determine the neutralino time of flight. And this definitely gives increased sensitivity, as we can see in the plot here. So you can see in the light blue curve the sensitivity increase thanks to MTD. And the other search for GMSB staus is here we are measuring the particle velocity beta, and here MTD improves the time resolution, and it allows to discriminate the signals or extract masses, as you can see. So here is 1/beta distribution, and then here is the mass calculation, which results from that. Now, coming towards the end, so we also have high mass resonances. Of course, that's usually the very first thing we look at, and there are several searches done for HL-LHC. So we looked at resonant di-Higgs to 4b. We looked at TT bar resonances for Randall-Sundrum gluinos. And then there are, of course, the usual Z prime and W prime searches in leptonic channels. So all are, of course, improving on the run-to results by several TeV. Now, there are also searches for leptoquarks, which could be important in explaining various flavor anomalies. And so there were several searches. One here is showing leptoquarks going to top plus mu or top plus tau, and the other one showing leptoquarks decaying to B plus tau. In all cases, so the different curves we are seeing are corresponding to different luminosities, and here we are looking at this expected significance versus leptoquark mass. And for a given leptoquark mass, we can see how drastically the increased luminosity is going to increase the significance. And finally, dark matter. We typically search for invisible dark matter plus visible mono object at the LHC. That's the most classical thing: monophoton, mono Higgs Z, mono heavy flavor, dark matter plus heavy flavor, or dark matter plus VBF. And interpretation is done with refined dark matter models with various assumptions of mediators, coupling to dark matter, etc. And overall, HL-LHC is significantly sensitive to heavier mediators and smaller couplings. And here I show some results from dark matter plus monojet and dark matter plus mono-Z searches. And well, I did not note them here, but with respect to run 2, there is plenty of increase. I think the monojet run 2 result was about 1.5, limit was about 1.5, and the mono-Z was 700 GeV, so about twice increase. And finally, on the right, we see dark matter plus heavy flavor searches. And so the results for different luminosities with ATLAS are shown by the colorful lines. The red line is showing HL-LHC. And this, again, increased sensitivity and provides good complementarity with direct detection experiments. So these are just summaries showing all the mass reaches, and this brings to my conclusions. So overall, HL-LHC is offering us a great unprecedented amount of data and new detector capabilities, and we are doing our best to explore it. And of course, there are still many ideas to explore, and we will keep doing so. Thank you.
Thank you, Sezen. Questions? Yes, Rohini, please go ahead.
Sezen, thank you for a very clear talk. I had 3 different questions. One was on your small mass Higgs. So can you go back to that slide of small mass?
This one, right?
Yeah. So one question I have, I mean, I guess this answer must be there in the strategy reports. How, because this is a singlet that is mixed, how does the possible limits compare with machine E plus E minus machine? Because the point is the mass is accessible in the low mass in the E plus E minus machines, but because of the singlet component, the rates are perhaps lower. So I'm just curious whether how does it compare? The potential.
Unfortunately, short answer, I don't have an answer. I have to check.
I see, but it might be interesting to know that answer is
Indeed, thank you. Yeah, I'll note.
Yeah. So that was one question. The second question was, can you go to your TT bar gamma slide?
Yes.
Yeah, here actually I think I didn't quite understand what's happening, because just let me. If I have understood it correctly, then we would save time. So let me say what I think I understood. That the dark red bars are, for example, the total uncertainty at 14 TeV, and the pink longer red bar is the 13 TeV. Is that the thing?
Yes, that's correct.
So the total, I mean, when I say pink, the length of the pink bar that I see is the length of uncertainty at 13 TeV, not the, how should I say this? So let me take an example. Let's take
the tallest one.
Yeah, the tallest one, but the height, not from the bottom, right? The height is only above the red one.
Well, correct? height, no, height from the bottom. So
I see.
Yeah. So it just allows you to compare the number at 13 TeV with number at 14 TeV.
So I can just compare the heights of the two. Okay.
Yeah, exactly. So what you have in between, what you see with light red, let's say, is the difference.
Okay, no, that's great then.
What you gain by
yeah. No, that's good to know, because sometimes one plots these separate, and then I should take the ratios of the two, but now I don't need to. Okay, great.
Can I make a small comment here?
Yes, please do.
Yeah, so you can see the statistical uncertainties in greens are very, very small. So it's mostly the systematic uncertainties.
Yes, of course.
Yeah.
Of course. That I think is clear. And also you can see the blue and the red comparison. Yeah, exactly. That tells you that. But what I had not understood was which now I understand, was
it
that
is
the
from the
total
bottom.
height of the pink is 13 TeV. That is from the bottom itself. So that means that for the tallest pink, for example, where there's something like 28% or 25%, that's the total uncertainty at, let's say, the 125 or 140 bit. So I think I understand that now, and thanks. And one quick question, Ritesh, if I may. You didn't talk about long-lived stows, Sezen, but in many SUSY scenarios, those are the most interesting ones, right? I mean, if you, many dark matter problem projects and these solutions. So you talked of long-lived muons.
Well, actually, yeah, I talked about GMSP stows briefly, as you can see here.
I missed it. Okay.
Sorry, I was sort of rushing towards the end.
I missed it. Okay. But other than that, what I meant was, not just GMSP, but in general, when you think of, light neutrinos, right-handed neutrinos, you do, modeling the different dark matter models, take an MSSM and add a right-handed neutrino. And then you can solve the dark matter very nicely. And the thing is, tau coannihilation plays a big role. So in general, long-lived stows can actually be very, how should I say, very common in SUSY interpretation rather than the long-lived muons. That is why it's the question.
Yeah, that's true. It's just that, especially for long-lived particles, the studies were done more to motivate the new detector features. And
all right.
Yeah.
All right. So, because taus will be very different than muons, right? I mean, that's why I asked this question.
Thank you, Rohini. Nistha Desai. Nistha Desai, go ahead.
Had a comment about this last comment of Rohini's about long-lived stows. The trouble with that is, I mean, if it is just a long-lived particle that goes all the way out, then the limits are identical to the stow, to the muon. But if it does decay inside, then you need to have a way of looking at, for example, very low PT taus and so on, which is kind
Exactly, Nishita. That is what I had in mind.
Right.
That is why I asked this question.
It's really an open question. Nobody really knows the answer to that problem, as far as I have figured out by talking to.
Okay, thanks.
Thank you, Rohini. Thank you, Nistha. Anyone else who would like to ask a question? Anyone else who would like to ask a question? If not, let's thank Sezen, and then let's thank both speakers of this session, Tuhin Roy of TIFR Mumbai and Sezen Sekman from Korea, for very good talk, lot of questions and answers, and thanks to Rohini for leading the question.